Okay, let's start. So it's a great pleasure to introduce Fiona Seibold from Imperial College, and she will tell us about supersymmetric integrable deformations of ADS3, S3, and T4.
Thank you very much, Ellie. And also first, let me thank the organizers for putting together this nice meeting and for giving me the opportunity to speak. So this presentation, as Ellie said, will be about supersymmetric integrable deformations of ADS3, S3, T4. And this is based on work that I did in collaboration with Hoare and Arkady Tseytlin, who are both in the audience today. So let me start by giving a motivation of why I want to study these deformed backgrounds. So perhaps you can be misguided by the number of talks that you will hear about integrable models, but usually those are very hard to find, especially string theories that are integrable and that have a good target space interpretation. And one instance where they seem to appear quite often is in the context of ADS-CFT, where you have several backgrounds that include the ADS factor that turn out to have this property of integrability. And I would like to, in this talk, to go a bit beyond the more supersymmetric backgrounds of this type and introduce deformation parameters. So this will be continuous deformation parameters that will allow you to go beyond these most supersymmetric cases. But since I would like to still be able to make explicit calculations, I would like to retain the property of integrability and also some amount of supersymmetries. From a broader perspective, the two questions that I would like to answer are the following. So the first question is, when you have a bosonic integrable background, so without any fermions, just a bosonic model that is integrable, when can you embed it into a 10-dimensional superstring theory that also preserves integrability? The second question is has to do with the interplay between dualities and integrability. So you know, for instance, that T-dualities, those are dualities at the level of the worldsheet, and those will preserve integrability for you. But in the context of supergravity, there is another type of duality that you can consider. This is this S-duality transformation. And you may want to understand, so we know that in some contexts, in some instances, this S-duality will preserve for you integrability, but we would like to understand a bit better when this happens and why it happens. And in order to understand these questions, in this talk, our playground for this will be the ADS3 cross S3 cross T4 superstring. So the plan of this talk goes as follows. First, I will show you some features of ADS3, S3, T4 that will be important for the rest of the talk. I will then present the deformed backgrounds that we found. In the third part of this talk, I will then argue that these deformed backgrounds are integrable, and this will not be immediate, but it will be made possible by making the relation with inhomogeneous Yang-Baxter deformations. So we have already seen these deformations in the previous days, and here we will use them in order to show integrability of these deformed backgrounds. Then, in the final part of the talk, I will discuss some interesting limits, and I will conclude and give some outlook, some open problems that still need to be answered. So let's start with the first part, and let me give you a brief, present some features of ADS3, S3, T4. So one important feature is that puts ADS3, S3, T4 apart from ADS5 cross S5, for instance, is that you can embed it into supergravity in different ways. So you can embed it into supergravity by, for instance, adding a pure NSNS form. So you just have H3 form. But you can also have, at the other end of the spectrum of possibilities, you can also have a Ramon-Ramon 3 form. So this is, the previous talk was basically sitting here in this pure Ramon-Ramon case. And you can actually have a one-parameter family of solutions where you both have the NSNS and Ramon-Ramon fluxes turned on. So this is the mixed flux case. and it interpolates between the pure NSNS point. So for this parameter Q is equal to 0, and the pure Ramon point where this parameter Q is equal to 1. You can, so this will be a one parameter family of backgrounds. You can do more. You can also add 3 parameters in the 5-form flux. This you can achieve by doing TST transformations. And all of these backgrounds turn out to be integrable, and they preserve 16 supersymmetries. So let's also look at the symmetries of the theory. So we know that ADS3 and S3, those are coset models. The symmetry group of ADS3 is given by 2 copies of SU1,1. So here, whenever I have 2 copies, I will label them by left and right. Similarly, for the 3-sphere, I have 2 copies of SU2. And when I include the fermions in the game, I will have this coset where the symmetry algebra, the isometry algebra is PSU1,1/2 left times PSU1,1/2 right. So this we already saw in the previous talk. So here I focused on the curved part of the background. So you also have the torus direction. So we had these factors of U1, but this is just the curved part. I focused on the curved part of the background. Okay, so this was some important features that will be important for the rest of the talk. And now let me start by deforming this. So we had this 1 parameter coming from the mixed flux plus the 3 from adding the TST transformation. So let us now add even more parameters by deforming these theories. And one, so also we would like to preserve integrability, and one deformation that we know preserves integrability is TST transformations. So combination of T-duality, a shift, and another T-duality. And this we can do whenever our background has 2 isometries. Now we're lucky because we actually have 4 isometries. So we have 4 factors of U1 sitting in SU1,1 left, SU1,1 right, SU2 left, SU2 right. Yes. On the yes, thank you. Yes, so this is a good precision. These 3 parameters here appear when you do a TST transformation in the torus directions. Okay, so we have these 4 factors of U1. So now we will do a TST in the curved part of the background, not including, we don't touch the torus directions. And we will be a bit clever because we know that we want to preserve some amount of supersymmetries. So what we will do is that we will select the U1 factors that belong to only one PSU1,1/2. So here I will deform the left copy, and I will keep the right copy untouched with the hope that then you will preserve the supersymmetries associated with this second copy. So let us do that. And so this is the metric that you obtain. So this is the metric, the deformed ADS3 factor, the deformed S3 factor, and here I just wrote the torus directions. And so let me give a bit more details about this metric. So when you have this deformation parameter kappa. So this one appears when you do the TST. You have 1 parameter, which is the shift, and this is basically this kappa. When you put kappa is equal to 0, this gives you undeformed ADS3 times S3 times T4. So maybe this is, you don't see this at first. This is because I chose here coordinates that basically make it obvious that, for instance, for the sphere, so this part of the metric, the sphere, the three sphere, you can see it as a S1 fibration over the 2 sphere. So this part of the metric is basically S2, and then you have the fiber Xi1 appearing here. And similarly, you have a similar story for ADS3, where you have S1 fiber over the Euclidean ADS2, or a hyperbolic space H2. And you see, now you do the TST, you turn on this parameter kappa, and you see that the effect of this deformation is to rescale the fibers by 1 plus kappa squared. So this is for the metric. Let's now look at the fluxes. Yes?
So does kappa have to be quantized in some sense here? Because of the coefficients of H3?
Because of the coefficients? No. So this is in the metric. Kappa is just a real number.
Right, but it's entering in the flux as well? So
Ah, yes.
So the fluid has to be integer or something, so is kappa quantized?
So if... so perhaps if you do an analysis at the quantum level, it will turn out to have some constraint on it. But for the moment, I'm just talking at the classical level. So I will just assume it to be a real number. Yes. So let's look at the fluxes. So for kappa is equal to 0, so we start from we deform the pure Raman-Ramon case. So we only have this Raman-Ramon 3 form that is turned on for kappa is equal to 0. And when we do the TST, yes?
The structure of
P hat
and B hat are different. It's not Vesuminiter.
Sorry, yes. Yes, it may. Yes. That's correct. Yes, that's true. So we have, when we do the TST, there is another, so there is the NSNS 3 form that turns on, and we see that there is a new 3 form that appears, this DB check, that involves the fibers in this way. So here, this is the usual 3 form that you have for the mixed flux model, that is volume of ADS3 plus the volume of the S3. And the new B field or 3 form that you generate, this will have a different structure. And similarly to the undeformed case, you could add additional parameters by doing a TST in the torus direction. So this was a simple, this was a toy model. We started from pure Raman-Ramon and deformed it. And what we saw was the appearance of these two different 3 forms. Now, these two 3 forms, they have an interesting property, namely their scalar product and their the scalar product with themselves and with each other is 0. So here, I mean, I contract the indices of the 3 forms. And this, from the point of view of supergravity, it basically tells you that it would be interesting to look at linear combinations of these two 3 forms. So we make an ansatz for the supergravity background that includes a linear combination of this dB hat and dB check. So I call the coefficients in front of dB hat by x1 by x, and the coefficients in front of dB check by y, and I populate the NSNS 3 form, Raman-Ramon 3 form, and Raman-Ramon 5 form. And I gather then, so then most of the supergravity equations of motion, due to this property, they're automatically realized, but you are left with one equation for the Ricci tensor, and this gives rise to 3 equations. So here I gather all the coefficients x1 to x5 into this vector x. I gather all the coefficients y1 to y5 into the vector y. And we are left with these 3 equations. And if these 3 equations are satisfied, then these fluxes supporting this metric, this is a good, so this solves the supergravity equations of motion. So let me discuss a bit more the properties of this background. So first, let us count the number of parameters that we have. So we had this kappa that appears in the metric. So this is one deformation parameter. And then we have the parameters appearing in the vector x and y that govern the NSNS and Raman-Ramon fluxes. So we have 5 in x, 5 in y. And then we have these 3 supergravity constraints. And this leaves us with an 8-parameter family of solutions. These backgrounds have interesting properties. So similarly to the undeformed theory, you will have a constant or trivial dilaton. so this is something that I didn't show, but if you write them in terms of a field-bound basis, the fluxes are homogeneous in the sense that they will be constant in that basis. And the geometry has a regular curvature and the vanishing reaches scalar. So this is very similar to what you have for the undeformed theory. Now, since we did a TST involving the left cartons, the lefty ones, we still preserved the symmetries in the right sector. So we still have the SU1, right times SU2 right. And in fact, you can show explicitly that this background preserves 8 supercharges, and these are associated to the copy PSU1, 1/2 that you do not touch when you do the deformation.
In the left, do you see that the cartons themselves?
Yes, sorry. You have times U1 left times U1 left. Yes.
Where you can define the energy.
Yes, you can. Yes, indeed. And one way to see these backgrounds that is useful is, and that also, where we have seen one example where this happens, you can see them arising from undeformed ADS3, S3, T4 by dualities. So combining T-dualities, so this in fact will be TST transformations, and also S-dualities. So in the context of my talk, by S-duality, I mean a rotation of the NSNS and Raman three-form fluxes. Now, the question we would like to answer is, what about the integrability of these models? So since it is a combination of T and S dualities, so we know that TST transformations, those we know they will preserve integrability. And in fact, there is a whole subset of deformations that can be obtained from undeformed ADS3, S3, T4 through T-dualities only. And those we know for sure they will preserve integrability. However, we also have many other backgrounds that, so the full 8-parameter deformation, some of them will also need a S-duality transformation, and this, a priori, we do not know whether it will preserve integrability or not. So we need to make a further analysis.
So do you know the conserved charges in this case? You know, have a Lux collection?
Yes, I will come to that. Yes. So in order to basically understand integrability of this model, it will be useful to see them not as arising from undeformed ADS3, S3, T4 through T-dualities and S-dualities, but through inhomogeneous Yang-Baxter deformations through T-dualities only. And this will prove for us integrability. So let me come now to this part of the talk where I discuss the relation of these deformed models with inhomogeneous Yang-Baxter deformations. So let me start by saying a few words about integrability in the undeformed theories. So we have the symmetry algebra PSU1, 1/2 times PSU1, 1/2. Algebra, it would be a plus. The Lie algebra has a Z for grading, and the Green-Schwarz string can be seen actually as a semi-symmetric space sigma model on the coset PSU1, 1/2 square modeled by the isotropy, so SO1, 2 times SO3. And so the action is of this form. So here the PI, so P1, P2, and P3 are the projectors onto the different subspaces of the Z4 graded algebra. And this is a group element. And the fact that you can rewrite it as a semi-symmetric space sigma model, this shows for you the integrability of ADS3, S3, T4 in the pure Raman case. Now, in the mixed flux case, you have a similar story, but here, because of this, so basically the fact that you have two copies of PSU1, 1/2, you can add a Ves-Zumino term to the action, and this will preserve integrability. so you can introduce this parameter Q, and this will actually show for you the integrability of the mixed flux theory. And then, so this shows that the mixed flux theory is integrable. And now we would like to deform this theory in order to preserve integrability. And this we can do using Yang-Baxter deformations. So this Yang-Baxter deformation will introduce will add 2 additional parameters to this action. So it takes the following form. So I didn't write it explicitly, but I give you the structure. So this Yang-Baxter deformation, you add this non-trivial operator between these 2 forms here. And you see that you have 3 deformation parameters, kappa left, kappa right, and Q. So this kappa left and kappa right, they deform the PSU 1,1, PSU 1,1/2 left and PSU 1,1/2 right copies. And this parameter Q is associated to the presence of the West-Zumino term. So, and you also see that there is this operator R that appears. So this is the same operator as Seibold was mentioning on the first day. This is a linear operator that is antisymmetric with respect to the bilinear form, so the supertrace. And in order to preserve integrability, we require that it satisfies the classical Yang-Baxter equation, which takes this form. So there are 2 classes of deformations that you can have depending on what this C is. So C is equal to 0. This places us in the context of the talk by Seibold, and these are homogeneous Yang-Baxter. This is the homogeneous Yang-Baxter equation if you just put the 0 here, and this gives rise to homogeneous Yang-Baxter deformations. So a particular subset of those are TST transformations and some deformed non-abelian T-dualities. Now, in the case of C different from 0, so when you have this right-hand side, this is the modified or inhomogeneous Yang-Baxter equation, and this gives rise to a new class of deformation, which are called inhomogeneous Yang-Baxter deformations. So let me give 2 examples. So there is another thing that I would like to say. One is that this action here, you can find the Lux connection, so that the equations of motion are equivalent to the flatness of this Lux connection. So this is a good indication that the model has classical integrability. Another question is about the Weyl invariance of these models. So when you have a string theory, then you deform it, whether you still end up with a Weyl invariant theory. And so there is this unimodularity condition that comes into play. So if you want to preserve integrability, then you have a unimodularity condition on this auxiliary Lie algebra that is constructed using this operator R in this way. And if it is unimodular, then it preserves Weyl invariance. So examples of this operator R. So you have the abelian R matrix. So it's abelian because you take 2 generators of your Lie algebra that commute. This solves the homogeneous Yang-Baxter equation. So this equation we see is equal to 0. It corresponds at the level of the worldsheet to TST transformations. So you do a T-duality in one isometry, you do a shift with this parameter S, and then you T-dualize back. And this operator is always unimodular, so it will map supergravity backgrounds to supergravity backgrounds. Another type of R matrix that will be very important here is the so-called Drinfeld-Jimbo R matrix. So how is this one defined? You take the Lie algebra, you decompose it into Cartan elements, positive and negative roots. This operator annihilates the Cartan elements and multiplies the positive and negative roots by plus or minus C. So C was this constant that appear on the right-hand side of the the classical Yang-Baxter equation. So this solves the inhomogeneous Yang-Baxter equation. So here I will take C different from 0. Another thing, so it is associated to so-called quantum group deformations. So you will, your symmetry algebra usually is deformed into a quantum group. The unimodularity, this of the R matrix, this will depend on the choice of Cartan-Weyl basis that you choose in order to define it. So, for instance, for PSU 2,2/4, that is relevant for ADS5, or for the purpose of this talk, PSU 1,1/2, which is relevant for ADS3 STT4 and also ADS2 STT6, you can show that unimodularity is present only if you consider the fully fermionic thinking diagram of these algebras. So, for instance, in our case, we need to look at PSU 1,1/2. This has 3 thinking diagrams. So here I denote this empty node is a bosonic simple root. This node with a circle is a fermionic simple root. So we have these 3 different diagrams depending on the number of fermionic simple roots that you have. And if you want to have a unimodular R matrix, you need to use the Cartan-Weyl basis associated to this fully fermionic thinking diagram. And if you do so, and if you start from a supergravity background, you do the deformation, you will end up again with a supergravity background. So let us do that. Let us apply this, do this inhomogeneous Yang-Baxter deformation. And maybe one thing that I should also mention is that, so we have these 2 factors. We have these 2 factors of PSU 1,1/2. We have these 2 deformation parameters. And in order to make the link with the backgrounds that I had before, which I told you preserve 8 supersymmetries, I will only deform 1 copy. So I will only deform the left copy. So I will put this kappa right to 0, and I will denote this kappa left by just kappa. Sorry. So if you do so, if you use this, you do this inhomogeneous Yang-Baxter deformation, then you obtain exactly the metric that you want. So this squashed or stretched ADS3 times S3 times T4. You will get exactly that. Now, for the Ramon-Ramon fluxes, this will depend on the explicit Drinfeld-Jimbo R matrix that you choose. But here, since we know that our backgrounds are supergravity, we will focus on the unimodular R matrix. So we will use the R matrix associated to the fully fermionic thinking diagram. And this gives rise to this background here. So we have NSNS 3 form, Ramon-Ramon 3 form, and Ramon-Ramon 5 form that are turned on. And exactly those V fields or 3 forms that appeared in the supergravity in the deformed backgrounds that I showed you previously. So we exactly have this structure appearing. And you can actually show that you can obtain all. So we had this picture before where you could obtain these deformed theories from undeformed ADS3, S3, T4 through T and S-dualities. And now we have another picture. We can actually obtain all of them through T-dualities only from this background here, from this Drinfeld-Jimbo deformation.
This is your insight, recent one.
Yes, yes. And this proves for you that the whole family is integrable. All right. So now that I showed you the deformed backgrounds, I argued that they are integrable. Let's look at some interesting limits. Let's see. So when did I start?
About 15 minutes plus maybe.
Okay, okay. So one limit is actually not a limit. It's more an analytic continuation that I would like to consider. So far, I always looked at kappa being real. But I could also look at kappa being imaginary. Now, in the metric, you've seen that kappa appears through kappa squared, so there is no problem there. I will preserve reality. However, if you remember, one of the constraints for the fluxes involved kappa without a square. So if I want to preserve reality of the background, I need to do some analytic continuations. So, and this is summarized here. And what this does is basically, instead of looking at ADS3 as a S1 fibration over the hyperbolic H2, it will just be a space-like fibration over ADS2 now. And the fiber will be deformed by 1 minus kappa tilde square. And so this is quite interesting because you see, so when kappa tilde is equal to 0, you still get ADS3 S3 T4, though in other types, not exactly global coordinates, but you still have ADS3 S3 T4. And now you can also take the limit kappa tilde going to 1, so that this fiber basically goes to, it shrinks, and you recover the ADS2 factor. So you get a background that interpolates between ADS3 S3 T4 and ADS2 S2 T6. And you can also look at what happens to the fluxes, and you get ADS2 S2 T6 supported by by a 5-ohm flux, for instance. So the usual ADS2 S2 T6 that you are familiar with. And throughout, so the whole line, so with kappa tilde between 0 and 1, the whole background is real and preserves integrability and the 8 supersymmetries. So this is quite nice.
Fiona, switching from real to imaginary, could it be interpreted at the level of real form of supergroups on which you formulate your theory?
So, like instead of having for the ADS3, instead of having SU1, comma 1,
exactly,
yes, probably, yes, yeah. Though, yes, probably, but you still have you still recover ADS3, so yeah. I'm not. The fermionate sector as well for the
super group, if you have a real form, if the real form and the bosonic sector are well classified, at the real form of the supergroup, I don't know whether they are as well. Yes, they are classified by Serganova.
So maybe it's a,
so maybe,
yeah.
Because
That's
the fermion contributes, to the.
Yeah, yeah, that's interesting. Okay, so yeah, so it's quite interesting that there is this family of background that interpolates between these two supersymmetric backgrounds, and that preserves 8 supersymmetries. So this, yeah. Sorry. Yeah.
It's good. Kappa is due to TST transformation, right? It's related to the shift.
It's related. So kappa is related.
Or?
So kappa is related to TST in the fibers in the left cartons of ADS3 S3.
It is proportional to gamma. Well, to the shift parameter.
It is proportional. Yeah. I mean, yes. You still need to make a coordinate redefinition. So I don't know exactly what the relation between the shift that you have and in the TST and the kappa. But I mean, they are related, but perhaps they are not exactly the same because you still need to do some coordinate.
So when you do this analytic continuation, gamma becomes purely imaginary.
Yes, it becomes imaginary.
But you also do analytic continuation.
Yes, yes, you also do.
Yeah. I'm just thinking about this Kazakov's models. When they take your imaginary gamma and send gamma to infinity.
The fishnet model.
Fishnet models, right? Is there any relations here?
I don't know.
Okay, what happens if you send kappa tilde to infinity?
Well, but we would like to stay within 0 and 1 in order to have a real background. So yeah, I mean,
so
I know
the background is not real anymore.
Yes,
if
yes,
kappa is greater
yes,
than 1,
yeah.
kappa tilde.
You lose. But yeah.
Okay, thank you.
Thanks. This interpolation, is this only happening in ADS3, or can you do the same thing on ADS5, ADS4? Because I think the question is, the TST I can view as a beta deformation there very concretely, and then can I match this from going from beta real to beta complex, for instance?
What you ask is that you can go from ADS S5 to ADS S3 in the similar way as we did it now, from 3 to 2.
So from ADS3 to ADS5, for instance,
From
or
ADS5 to
to
ADS3.
ADS4.
Maybe we are pushing here too much.
Yes.
There is a calculation to be done.
I just have a comment that I guess that here you use crucially the fact that you have this factor.
yes, of course.
And one factor is related to having ADS2, and that will not quite be the case if you try to go, let's say, from ADS5 to 4 or ADS3, that is 4 to 3.
Yeah, it depends whether you can have pop vibration.
Yes, yeah.
A little bit more subtle.
Good. So let me now consider another limit, and this is to make the link with Jordanian deformations, so a homogeneous Yang-Baxter deformation. So you take, in some limit, you can recover the three-dimensional Schrödinger spacetime, so deformation of ADS3 in the Poincaré patch, with undeformed S3 plus the torus T4. And similarly to what was done here, where you infer integrability through the relation with inhomogeneous Yang-Baxter deformation, this you can also, so you can also infer integrability from starting from a homogeneous Yang-Baxter deformation, so a Jordanian deformation, this Jordanian deformation with the fermionic tail that Seibold was mentioning on Monday. And another perspective here is that this homogeneous Yang-Baxter deformation, you could also see it as coming from ADS3, S3, T4 through non-abelian T-dualities. Another limit is the PP wave limit. So you look at the geometry seen by a particle that moves along a geodesic, so on the a great circle of S3 and also in the time direction of ADS3. And this is the metric that you obtain. And you see that it takes the usual plane waveform. So this coefficient J goes from 1 to 4. And this would be your, so Z1 and Z2 would be associated to the ADS bosons, and this would be associated to the bosons in the sphere. And you see that what happens at the level of the fluxes is that the three forms that you have, they actually coincide. So everything only depends on the linear combination of x1 and y1. And so you can see this as the geometry seen by so these four free bosons that are massive, and you can compute their dispersion relation, and you get this nice formula where omega is the energy, p is the momentum, and you have two types of particles that are left or right. So this is similar to what we had in the previous talk, and you see that something interesting happens when this x1 plus y1 is equal to 1 plus kappa squared, because then this dispersion relation becomes linear. So you can write it in this form. And so when kappa is equal to 0, you get the usual linear dispersion relation of the pure NSNS ADS3, S3, T4. And you will also have a similar structure while turning on kappa now. Okay, yes. So these are the three limits that I wanted to briefly mention. And so let me now come to the conclusions and the outlook. So let me summarize a bit what I did in this talk. So we constructed an 8-parameter family of supergravity backgrounds that have a deformed metric supported by 7 parameters that control the NSNS and RR fluxes. Depending on whether we take this kappa to be real or imaginary, we had 2 types of deformations. So the 2 types of deformation, and so we had some interesting properties that are similar to what we have for the undeformed theory. Namely, we still have a trivial dilaton, we have regular curvature, we preserve 8 supersymmetries, so we will break half of them, but we still have some good control. And these theories are integrable. We have seen 2 perspectives on these deformed theories. First perspective is looking at them as deformations of, them as obtained from ADS3, S3, T4 through a combination of T and S-dualities. And this is not very convenient when you want to investigate integrability, but there is another perspective that is interesting, and this is when you make the link with inhomogeneous Yang-Baxter deformations, and you can then obtain the whole set of deformations through T-dualities only. And this provides another example where this S-duality transformation, so just this rotation of the NSNS and RR 3 preserves integrability. So this is an example now in the context of inhomogeneous Yang-Baxter deformation. And in fact, similar observation was made in the context of homogeneous Yang-Baxter deformation. And it seems that this tends to happen in all those cases where it happens, you have trivial dilaton and vanishing Ricci scalar. So this is a property that you seem to be required for S-duality to preserve integrability. Let me also mention some open questions. So first of all, one interesting question in the context of ADS-CFT has to do with the brane geometry. So we know that for the mixed flux case, or the pure NSNS, pure RR, we have a good understanding that these geometries, they can arise as near horizon limits from a brane configuration. And I mean, it would be interesting to understand whether the same happens for these deformed backgrounds, whether we also can find some brane configuration, take some near horizon limit, and end up with these deformed ADS3, S3, T4 geometries. Another question has to do with the symmetries of the deformed theories. So when you have this inhomogeneous Yang-Baxter deformation with 3 deformation parameters, so we kind of know that when there is no Wess-Zumino term, the symmetries have been analyzed in quite detail, and we know that they correspond to Q deformations, so quantum group deformations. But when you add this Wess-Zumino term, there seems to be some tension with that observation. Also, when you want to obtain an exact S matrix based on the symmetries, then you compare with the results from perturbation theory, and I mean, you cannot really find an agreement. So, yeah, what's happening to the symmetries? And so I briefly mentioned the geometry in the PP wave limit. You can, starting from there, you can compute the 3-level perturbative S matrix. But you can, as I said, also try to use once you understood the symmetries, you can try to construct an exact S matrix and then check integrability at the quantum level and apply the whole integrability machinery. And an interesting question has to do, is in relation with this work by a group in Dublin, and I don't know if you heard the talk at IGST from Anna, but they have an S matrix, an elliptic S matrix that interpolates between the ADS2, S2, T6 and ADS3, S3, T4 S matrix. So, and here we have a background that does that, so what is the relation there? And finally, another question has to do with Poisson-Lie duality. So this is something that I didn't mention in this talk, but this inhomogeneous Yang-Baxter deformations, or eta deformations, they're also called. They are Poisson-Lie, so they have some special symmetry that is called Poisson-Lie symmetry, and they are Poisson-Lie symmetric to these lambda deformations that Dan was talking about yesterday. And so this is fairly well understood for when you have one deformation parameter, and then it would be interesting to see what happens when you have the whole 3-parameter deformation also, perhaps with Vesumino term. So yes, so that's the end of my talk. Thank you very much.
Questions?
Fiona, thanks for a nice talk. So at some point you mentioned a little bit about, at the beginning you started by saying you would like to understand a bit about when S-duality can preserve integrability. Then at the end you said something like, okay, it seems we can do this in the cases where there's no Ricci scalar and so on, and that seems to be a constraint. But I mean, it's also clear that you were able to play this game exactly because you were in this restricted setting, right? That's why you were able to find these backgrounds and show that they're related to integrable backgrounds. So can you really, can you say something more about like excluding other cases? Like, can you show that it's impossible to have integrability or something in some other case where you have S-duality, or?
No, so from this analysis, I don't think you can infer anything about more general cases. And yes, I mean, for this, also to make sense of S-duality as just being a rotation, you need to have trivial dilaton. And I guess, assuming trivial dilaton, and then also assuming that you have homogeneous fluxes, basically having a null Ricci scalar, this is an automatic conclusion of these two constraints. So yeah, yes. I mean, this is another example where it happens, but I cannot say anything about more general cases. Let's say.
Okay, and now you have some larger list of examples. So now you have various kinds of transformations that in the end are related to S-duality. Is there, can you factor out the S-duality and represent it as a chain of other things in some nice way now, or do you not have enough structure yet to see that?
So see, okay, so see precisely at the level of the, so do you mean like see precisely at the level of the inhomogeneous Yang-Baxter deformation, what transformation really is associated to this S-duality?
Yes,
yeah, I mean, I didn't look at it, but it's probably a setting where this can be understood, can be analyzed.
Okay,
yeah.
that would be
You
great.
can ask this question already for the H3 plus F3.
Yeah, just undeformed.
You get some rotation, and you can, S-duality will be some
Mm-hmm.
action on this parameter Q. That's all.
Yep, thank you.
Someone else?
Do you have a geometric interpretation for this transformation with kappa squared less than 0, similar to
So kappa square less, yeah, so imaginary, so this is deformation of the, I mean, this will be deformation. So this analytic continuation, you don't do anything on the sphere. So this will again be deforming the fiber, but before we had 1 plus kappa squared. Now it will become 1 minus kappa squared if you think of kappa as just being real.
I mean, can you implement this kappa squared less than 0 transformation on the level of the string sigma model as a transformation of string fields?
Yes. So you need to do, yes. You need to start from writing ADS3, S34 in another set of coordinates where you make apparent that you have this fibration over ADS2 now. And then you do I think you should do the TST in another type of fiber that is space-like instead of time-like, and then you should end up directly, I hope, with this background with kappa square less than 0.
So you think it's going to be again a TST transformation?
I think it will again be a TST transformation, just different.
No more questions? Okay, let's thank Fiona again for the very nice talk.